So I'm Matt Tolman. I have been using WebAssembly mostly in side projects and hobby projects for several years. Started using a lot of the tool chains before there was WebAssembly, back when it was ASM.js and WebAssembly was being standardized. So I've gotten to see a lot of the evolution of this idea of taking something like C or Rust and compiling it to run on the web. So first off, what is WebAssembly? WebAssembly is a bytecode format that you need a runtime to execute. So think of this as more of JVM bytecode, where you have to have a Java runtime rather than something that you're running on the CPU directly. This runtime comes in your browser, and it's designed to be restricted. So it can't access the DOM, it can't manipulate the network, it can't do those things directly. There's a couple reasons for that. One was this was coming back out of the days where you had Flash, Java Applet, Silverlight, and there was a lot of security issues with those. And so they were trying to lock down this new runtime and be more secure. So they made it so you can only have numbers as inputs and outputs for functions. They did design it so that you can have a host language. In the case of the browser, that's JavaScript, and the host language can then do actions on behalf of WebAssembly. And so that's how you can have WebAssembly frameworks, which allow you to manipulate the DOM as they defer to JavaScript. And then WebAssembly was made to be fast, especially when it comes to things like numerical computations and bit operators. On the left here, I have some WebAssembly code, and we have a function main, and we're exporting it. When you export it, that function can be called from your host language. So you can write a function in C++ or in Rust, and then use it from JavaScript. When we load WebAssembly, we fetch the WebAssembly function, and then we instantiate a runtime. That instantiate is asynchronous. So you're going to get a promise back and you have to wait that promise. That can be a little new when you are first learning WebAssembly, since you're used to when you load JavaScript code, it's ready once it's loaded. But here you have to load it, and then you have to wait for a runtime to come up. And the more WebAssembly you have, the longer it'll take for the runtime to parse it all. Once you've loaded it, you can call any methods you've exported. When we talk about how WebAssembly can be fast, often we have charts like this. This is from a project I did about 1.5 years ago, where I took a random number generation library called TinyMT, and I ported it from C to TypeScript, and then I recompiled the C code into WebAssembly and compared the two. And my WebAssembly code was significantly faster with all these number calculations. TypeScript was about 500,000 random numbers a second, whereas WebAssembly was 6.5 million. So good performance increase. One of the things I want to cover, though, in this talk is how these benchmarks in their own, it can be misleading. This is a very good use case of WebAssembly, and there's other use cases where it's not going to be as high, and we'll have more benchmarks later on. But first, I want to talk about some of the tools you're going to use when you use WebAssembly. And these are going to be different tool chains. Tool chains are basically a compiler that's been modified to take a programming language, compile it to WebAssembly, generate some JavaScript code along with that WebAssembly executable. And then that JavaScript code does a lot of bindings. It does a lot of initialization. And so you're not calling WebAssembly to instantiate directly. Your tool chain will generate that call for you, and it will add in things so that you can call JavaScript code. You can export complex types with strings and classes. You can transition between WebAssembly and JavaScript, and they provide a lot of functionality. None of that's magic, and we'll cover how that happens behind the scenes so you get an intuition of what is the cost that you get with these tool chains. But it is very convenient to use when you're doing WebAssembly. So this is an example of some C++ code using mscript. And mscripting is the oldest toolchain I know of. It was made in 2011 was its first release. So it is definitely old in the web world. It is older than Webpack by several years. With mscripting, you include the toolchain, and then you can have C++ methods. You'll notice that we have standard string. This is the C++ standards library. And so we're able to take a string as input and give a string as output. And mscripting handles translating JavaScript strings to C++ strings and back again for you. And then at the bottom, we have binding saying, hey, I want to export these methods, and these are the names to export them as. When I say mscripting is old, I do mean it is old. It predates Webpack, so it doesn't have the concept of modules and imports and exports that you would have in modern build systems for JavaScript. Instead, it relies on the old style of doing everything in global variables. And so we have a global variable that we declare called module, and that's where all of our WebAssembly code will live. We then do an on runtime initialize callback, and that's the entry point for your application. Once it's loaded, it's WebAssembly, it'll call that function and start running your code. And so it'll add any exported methods to that module variable, and you can call them. You then have a JavaScript file that it generates that you then import with a script tag after you've declared your module file. And that's how you use mscripting code. It works great for legacy systems, but a lot of people want something a little bit more modern. And Rust provides that, both with a more modern language, and also it has proper ESM module support. So here, same code, just we're doing it in Rust. We have a compiler macro. And then since we have full-on ESM modules, we can just use our import statements and import our code from the generated JavaScript. This works much better with modern, Webpack and bundlers and things. Since it is still asynchronous, we do need to await an init function, and then we can call our imported code as if it's JavaScript code. And as we can see in the output, the type of our result for greet is a string. So it is behind the scenes taking your Rust and C++ strings and converting it into a JavaScript string for you. Both toolchains do allow you to export classes and structs. Yep, I can see some hands. Correct. It is compiled into WebAssembly, and then the browser is loading that compiled code and running it in its own runtime. Yeah, so it's not like you compile it directly to your CPU. It's being interpreted. Perfect. So yeah, you can export classes and structs. You can export properties and methods and getters, setters, all that stuff that you would expect can be exported. And then you can use those in your browser, and you can create new instances of your class. You can do instance of checks. You can access properties as if it was a JavaScript class. The only difference is we have these destroys and frees, which begs the question, why do we have destroys and frees? I thought we were in a garbage collected language.
Well, I would presume that we're not in a garbage collection language because we're
Well, even if you use Go, you have this. Is less of a language issue and more of a WebAssembly memory model issue. So this is something that is due to how they're getting around that limitation of you can only have numbers in and numbers out. They're passing these strings, they're passing these classes, but they have to still work within this limitation. And the way they do that is they use memory addresses. And so what they've done is they've given JavaScript read and write access to your WebAssembly heap, your memory inside of your WebAssembly runtime. And so you can pass a memory address saying, hey, I wrote a string to this location. And then JavaScript goes in, reads those bytes, and then copies those into a JavaScript string. And that's how you get the strings out. And then when you want to go back, you write the string to memory and then pass in that address that you wrote it to. Like the primary advantage of using multiple memories. The answer is yes and no. So speed sometimes, yes. If you have a lot of calculations that you're doing in the browser, like you're running a physics engine, then yes, you might need WebAssembly to be able to do, thousands of entities in the physics engine. If you are trying to use an old library like FFmpeg in the browser, it's really hard to port FFmpeg over to JavaScript by hand. And so you might just say, it's cheaper for me to compile it to WebAssembly and bring that into the browser.
About these tool chains, there's really two parts they get executed. There's like the WASM code, and then there's like the boilerplate about essentially the report and stuff like that. Is that what it is?
Yes, exactly. And so there is those two halves of it. You have your WebAssembly code, and that's what your compilers would normally think of. And then you have this JavaScript binding logic. And your traditional C++ compilers like GCC and Clang don't understand how to generate JavaScript code. And so they bring in extra build systems and modifications to generate JavaScript that can read the memory and all that stuff. For classes, our memory gets a little bit more complex. When we export a class, the functions and those methods for that class still live within WebAssembly code. We didn't convert those into JavaScript code. And so when we call those methods on that function, we have to tell WebAssembly what data to operate on. So we keep our data for those classes and structs we're exporting around, and we're just passing addresses back and forth. So we're not necessarily copying it out, but we keep a hold of where that is in memory so that we can then pass that back to WebAssembly and say, hey, go access this property or this method on this address. And this is a simplified view of what that'll look like. I will break this down because it is a lot of code.
But this is like this.
Normally you wouldn't write this. I did write that by hand, but normally you wouldn't. This is what your tool chains would generate. And so what they'll generate is they'll generate this import statement. And this import statement says, hey, I need some extra thing from the host that I don't have myself. By default, WebAssembly can't go access memory. It can't allocate memory. It's locked down in that way. It has to ask the host language, give me some memory, please. And if the host says, no, you're done, well, now you have to throw an exception saying, hey, I couldn't get memory even though I asked for it. So this lets you put limits on how much memory it can use. Once you have your memory, when you create a class or struct, you need a location. And I just did a very simple allocator where I just store the next address in some byte, and I just say, hey, pull out that address. Generally, you're going to have much more complicated output from your allocator, but you don't care about that because that's handled by your tool chain for you. Once you have the address, you populate the bytes at that address. And so you say, hey, I'm going to put my ID at offset 0 and my value at offset 8. So I'm doing, 8-byte alignment. So, just what your programming language would do. And then you return the address of where you wrote that. Then when you have your getters and your functions, you take in that address and then you operate on that address. And that's essentially how you make a struct in WebAssembly. Just a lot of addresses and offsets. JavaScript code is a lot cleaner. We just create some WebAssembly memory, and this is where we can say how much memory you start with, what's your maximum memory, and then we pass that in to this environment when we instantiate it. And this will auto-wire into where we imported it, and then we can access it from WebAssembly. Then for niceties, we'll often create a wrapper, and that's what your toolchains are doing behind the scenes, is they're creating a wrapper class to make it look like you're calling JavaScript class methods. And what this will do is this will just manage that address for you and pass it in and out. And then you can call it like you would any other JavaScript class. So that's what's going on behind the scenes for this code. The advantage is we're not doing a full copy, so it's not nearly as expensive. The disadvantage is now we're sharing memory, and our WebAssembly code no longer knows when it's safe to free up that memory. It's returned a pointer essentially to JavaScript, and it doesn't know when JavaScript's done with it. And so it can't just free up that memory anymore. JavaScript has to say, hey, I am now done with this memory address. It's now safe to clean up. And that's where we got the destroys from. So this is something you have to deal with any language, even if it's a garbage collected language like C#. Toolchains have ways to hide this from you, which we'll cover. But it's important to understand that this is kind of what's going on under the scenes. Hopefully soon, this will go away. There is a proposal that's been accepted, but not part of the standard yet, where you can tell the JavaScript engine, hey, I want your garbage collector to manage this piece of memory. And then you just clean it up when you're done. And that would make this whole problem go away. And so a lot of tool chains, what they've done is they said, well, this is going to go away at some point. So we're not going to give any workarounds to make this more pleasant. And we're not going to document it very well because ideally this is going to go away in a few years. Until then, this is typically what you have to do to make it working well. Or just ignore the problem and hope you don't run out of memory. Correct. Once you refresh the page, you get a new instance of that runtime and the memory's all gone. And so if you're doing something like a traditional, you click a link and then it loads a brand new page, you probably don't have to even worry about that memory management. But if you're doing a single page application and they're never refreshing, then it might be good to worry about that. Just for those users who never close their browser tabs or refresh anything for months on end. So far, we peeled out how these toolchains are passing structs and how they're passing strings. Some of these toolchains allow you to access web APIs. And there's frameworks out there, so how are they doing that bit? Our WASM code is still restricted to no DOM, no network, no local storage, no cookies, none of that. What the trick is we need a way to grant access, and we do that by importing JavaScript functions. So that same import statement we use to import memory is the same statement we will use to import functionality. And this is an example importing a JavaScript method. We have this type declaration here saying, hey, this is the type of what I'm going to import. And this is where we declare our contract saying, I'm importing a function that takes 2 integers and returns an integer. I'm going to import it from my host namespace with the name add, and I'm going to call it add. And then later in my code, I can call that function add and pass in some variables. On the JavaScript side, we declare the function add, and then when we instantiate our WebAssembly, we just pass that function in, and now we can call it from our WebAssembly code. We can do anything we want to in this function so long as it complies with this interface. So if we wanted to add console logs or update the DOM or do an alert, we could do all of that. And when we combine that with the toolchain's ability to export classes and strings, we get something really powerful. Ideally, though, we're not writing this code by hand. And so what toolchains give us to solve this problem and our previous problem is inline JavaScript. So we can have parts of our, in this case, C++ code where we say, hey, I'm going to write some actual JavaScript. It's going to take a standard string as input. And then this is the JavaScript code I want you to execute. And when you're doing your coding like this, your toolchain knows when the JavaScript code is done running. And so it can manage inserting those destroy statements for you. It can also allow you to just write JavaScript code that is sitting next to your C++ code, and it will handle creating those imports and the bindings for you.
Wow, this is mind blowing. Can you go back on slide?
Absolutely. Oh, wrong way.
So this is add function in JavaScript side. Do that get compiled, or you're saying it's imported?
It's imported. So any stuff you declare here is imported. If you're going to put in like systems programming terms, imagine you're saying, hey, I'm importing a shared library that has this function. I don't know what that is. I'm going to let the operating system handle loading that shared library and setting everything up. What we're doing is we're saying, hey, JavaScript, I need this function. I don't know where it is. You figure that out. And so our JavaScript code here is, okay, I have this function, and now I'm figuring out how to wire that in. What our toolchain does is it says, hey, I'm declaring this JavaScript function. It's like, okay, I'm going to take this code, extract that out and put it in JavaScript land. And then I'm going to create the binding and the glue that wires what I put in JavaScript land and let you access that in WebAssembly land. So it's automating the step of declaring these imports, declaring this function, and then wiring that function in. And that all is handled with this one ESM.js macro.
Basically, somebody's gonna execute, and then when we get this sort of function, it's gonna stop and say, hey, okay, you need to go ahead and execute this function and on bait. And then it relates back and so they can still, right?
Yes, exactly. Yeah. Once we hit this say hello, we're now leaving WebAssembly land, going over to JavaScript, running some JavaScript code, and then we come back to WebAssembly land and go to the next line. And it handles this transition from WebAssembly to JavaScript and back again for you. And this is the secret of all these WebAssembly frameworks like Blazor for C# and Vue for Rust. And I think there's one out there for C++, but nobody uses that. So what they do is they just create a lot of these bindings and this context switching so that you can write code which looks a lot like React or Angular in Rust or C#, and it generates all the JavaScript web API wrappers, binds that to your WebAssembly, loads your WebAssembly, passes these classes and structs and strings through heap memory, and that's how you get a string from Rust and these HTML tags out of WebAssembly and into the browser. They just took all of those building blocks we used and did it at scale. And so they have not just one or two functions manually bound, but they have somebody who's made a framework where they're binding thousands of web APIs.
Or is it something that's compiled like JSX?
Great question. I am not a Rust expert. All I know is when you use you basically get JSX-like syntax. How it works, I'm not quite sure. I picked Rust because it's way more popular for this type of full stack front end thing than C++ is. I'm much more familiar with M scripting and C++. So, but C# and Blazor has something like this too as well. And then they also have it where you can even do server render components and WebSockets and all sorts of stuff. So at this point, we can do anything we want to in WebAssembly. So we should, right? Not quite. We'll go back to this benchmark. I've been hinting at this throughout, but this benchmark is the best case scenario. It is only numbers, so there's very minimal overhead, and we're not switching back and forth. We're not copying. We're not importing. We're not deferring to JavaScript. And so all we have to do is add a few of those, and this gap will drop dramatically very quickly. And we just have to do a little bit. We're just going to do random string generation. We're just going to concatenate some strings in JavaScript. And I'm going to show you two C++ examples to give you a range of performance. In this code, I'm just using math.random. In my actual benchmarks, I use my tinymt because I wanted to benchmark the exact same algorithm in both. So when we see the numbers, just know we're doing tinymt for everything. On the left here for the C++, I have the clean code way. We're using the C++ version of a string builder. Basically what a string builder is you have a class, you say, I want to add all this stuff. I don't know how much I'm adding. I just want to add a bunch of it. And it handles doing that in a efficient way for you. And then you can say, all right, now give me a final string of everything added together. On the right, we're doing it like C. We're doing a malloc, we're doing null terminated strings, and we're doing pointer arithmetic to just fill up that array with bytes. This is the benchmark using tinymt for everything. 55,000 random strings per second for TypeScript. These are like, 1,000 character long strings. 25,000 for a clean code way in C++, and 65,000 for a C style of writing things in C++. That is quite the difference in performance just doing a small change. We're going from magnitudes faster to either half as fast or a tiny bit faster. And the reason is performance is just really nuanced once you get to WebAssembly. When you have a lot of overhead in transitioning and you're doing those memory copies and you're going from one runtime to the other runtime, those transitions take a lot of performance. And if you think about what the CPU has to do, you're going from running one JavaScript engine to, okay, now I have to unload that entire engine from memory, go load WebAssembly engine into memory, figure out where I am in my WebAssembly code. Okay, now I can start running that. Okay, now I need to put that all away, go reload my JavaScript engine and start that up again. That's quite a bit of overhead. And when you compare that to what the browser provides, the browsers are really well optimized. They've had over 30 years of JavaScript development to get their engines really well tuned. And they have lots of built-ins. You do string.contains, that's not running some sort of arbitrary JavaScript library. That's running C++ code optimized for how that JavaScript engine represents a string in memory. That's really, really hard to beat. The other thing to keep in mind is, well, WebAssembly is running in its own runtime, and that runtime is much younger. WebAssembly wasn't standardized until 2017. It's had less than a decade to develop engines and optimize engines, whereas JavaScript has over 3 decades. That's a huge disparity. So when you try to replace everything with WebAssembly, you tend to get lackluster performance. The other side of this is that WebAssembly was never meant to replace React. It was made well before React. It was meant to just do number crunching in the browser quickly. And there's a lot of examples, and my favorite is the one I found, which got me into WebAssembly, back from 2012. And this is called the Banana Bread Engine, and it is a 3D first-person shooter game engine with particle effects and smoke and all this stuff running in the browser. Back from 2012, and it's running really well. We're hitting 60 frames per second while I'm doing a screen share. And they have AI, they have physics, and I'm not very good at it, but it inspired me. Some people have on their blog, this guy has a Monte Carlo simulation that you just hit a button, runs a simulation, just like that. And Monte Carlo simulation, for those who don't know, is a financial analytics thing where they do a lot of random numbers and they use those random numbers to try to figure out how would a financial portfolio, perform in the future. I don't understand all the details. I just know there's a lot of math and numbers. A couple that I did are here. I haven't done too much impressive, mostly because I'm not much of an artist. But this is a written in C using SDL. This is a maze generation. And I have a thing where it will calculate the distance from where you're at to every cell. And as you move, it live updates that calculation. And it does path finding and finds the shortest path. And we have a bunch of different algorithms that have different metrics. So those types of, hey, I'm doing a lot of calculations all at once, WebAssembly does really well for.
And really those standards that on top of this, and who has somebody to the WebKit browser, you put it through JavaScript. And so inside of a universe, you could run a browser.
Yeah, and we're actually going to show some of that off too, because that brings me to the next one is porting old apps and libraries to the browser. One of these examples is FFmpeg. We can come here and somebody's taken FFmpeg. They made a little JavaScript HTML wrapper and we can load some sample files. So we've loaded a WebM and then we can scroll down a little bit, hit run, and now that's running FFmpeg to convert that WebM into MP4. Running in the browser, no server, just right there. Another example is the Godot game engine. We can run the entire Godot game engine. It's remembered a empty project I made before I got here, so we can load that up. Sometimes it's a little slow. It's running an entire engine. We have autocomplete, and we have an entire 3D view that we can move around in. So you can make a video game in your browser with an actual full game engine. I didn't take it apart. I just know that, but most likely, yeah, it's you either doing Canvas or they did a lot to wrap that in. Yeah, they most likely are doing Canvas. Most of these are Canvas. So like my maze game is definitely running in the Canvas. Yeah, I'm using mscripted. And so all I did is I wrote it like I would a normal video game. I wrote it using SDL. And then I told mscript, hey, just include SDL. And it's like, okay, I know how to handle SDL. And it translated it into Canvas calls. And it can also translate OpenGL into WebGL calls, which is how they did that banana bread game. Another use case, which is cropping up more, is this idea of, well, why is it that only the developer can run random programming languages in the browser? Why can't we let the user run a programming language in the browser? So this is Python 3.12.7. This is PyODide, which has been around for a while. The creator behind this has done some amazing work. And you can do x+1 for x in, we can do our list comprehension, and we're running Python. You can take this, put it into something like LeetCode, and now instead of having to have complicated server infrastructure with virtual machines anytime somebody tries to run their code, you send the runtime to them and it just runs on their machine. Yeah, they just took C Python and compiled it to WebAssembly. And the C Python is the reference Python implementation. Yes. So we're running Python. This is full Python. You can see it's compiled with Git. with Clang. This is the version. The guy behind Pyodide did that's what this project's called. He's done a lot of work to get Python running in the browser, and it's really impressive. People have taken this idea of, hey, wait a second, we have a runtime that by default is isolated. Why are we bothering with Docker? Let's just create some extensions so that your WebAssembly can be a web server. And so they've created standardized extensions that you can enable with your runtime by doing command line flags saying, yeah, give this binary network access on this port. And you just import that functionality like you would a JavaScript function. And so you can run WebAssembly as your server. And the idea is to replace Docker containers and AWS Lambdas with something a little more lightweight with WebAssembly. Docker themselves has WebAssembly workloads where they are trying to use WebAssembly to run inside of Docker runtime alongside your normal Docker containers. So there's a lot of really cool developments. Not any of the ones that are interesting are meant to replace React. This is all meant to go alongside what you would normally do. You know, you're not going to be writing your whole website running in a canvas, and you're probably not writing your website where you're doing WebAssembly methods to calling out to your DOM. You're going to have like a number crunching library of, hey, I need to do this video encoding, or I need to run this physics simulation in the browser, and you'll defer to that to do the calculations, and then you'll use React to show the result.
Can you run Unix in the browser?
I am sure somebody has that. I know there is a project to run Linux in the PDF. The reason they can do that is you can actually have JavaScript in PDF files. And so they compiled a subset of Linux to run in PDF, and it is awful to use. Do not recommend it. If you're interested in learning more about WebAssembly, these are resources I have used. WebAssembly.org is the official site. They have links to other resources like MDN docs. They have the official spec. Really great if you run into weird edge case and need to figure it out. Mostly, though, it's designed for people implementing tool chains and stuff. Mscripton is the tool chain I'm personally the most familiar with, mostly because when I got into WebAssembly, there weren't really any other tool chains. That was the option. Since then, there's a lot of other tool chains, and Rust is a tool chain that has come a long ways really quickly. If I was learning WebAssembly for the first time, that would probably be where I would start. They have a really good online book that covers a lot of material, from how to export classes to, hey, we actually created our own garbage collector because we got tired of waiting for that garbage collector proposal. So this is how we did our own garbage collector for your WebAssembly memory. This is the limitations of it. We still have that free function for those limitations. And also, this is how you can package your WebAssembly code publish it on NPM so other people can use it like they would a JavaScript library. So really cool stuff there for the Rust people. I do have a blog post which basically covers the experiments I showed off in more depth. It goes more into the benchmarks and more into the details of what I learned along the ways. Wasix.org is great for that whole WebAssembly for the server, running it as a replacement for Docker. It is still early technology, so be warned, it may not quite be production ready yet, but it might be fun to play around with. And then Impractical WASM is a good tutorial I found for getting you started in how to read and write WebAssembly by hand. It won't get you all the way there. Some of the stuff like imports and types, I had to figure out what was going on my own, but it will get you quite a ways there. I have posted these slides online at talks.matthewtolman.com, so you can go there and click the links. My server hasn't been acting out a little bit lately, so if it's down, I apologize. I am going to transition from the current static file server to a different static file server that's been more reliable. I just didn't have time to do that before I came here. So any questions for me?
Nothing that I wasn't to JavaScript exactly, like you could create the runtime that was using WASM and WASM standards, but it's actually non-JavaScript program.
Correct.
Are there any?
There are a couple. So if we go back to WASX has the one that I'm the most familiar with. Well, they don't have the runtime. They use WASMer as the runtime, and WASMer runs from the command line. So WASMer, this doesn't use necessarily a host language. This uses command line parameters instead to grant access. So it's not designed like, oh, I'm going to create my spa. This is, oh, I'm going to create my server, and I'm going to say it has access to this file system directory. There are some experiments out there to do cross-language libraries where you write one library in C++ and you use it in Java, and WebAssembly is the common language. So instead of using C ABI for everything, you use a WASM ABI. I didn't go into too much depth for those because most of those projects are really early on, and it's really funny trying to get tool chains to work well with them. So Rust has much better support for these newer types of things. C++ also has some support. I just had a hard time getting it to work, so I haven't used it much. So yes, there are things out there. I don't have much experience with them, which is why I didn't touch on them much. I know of them, I just haven't used them. You know, it is a great question. I wish I was in those meetings. So I got into this whole WebAssembly thing with ASM.js, which is asmjs.org. I've read through the ASM.js spec. They say work in progress. It's been superseded. They just haven't updated it. But this is, hey, we're going to create a subset of JavaScript that you can compile to. It's the bare minimum we need to have something assembly-like with 32-bit integers. And then we're going to use you know how you have like the quotes use strict? They had a quote like use ASM. And that would tell the browser this function is an ASM.js function. And so you can hyper-optimize it. And they do some really weird things, like you would compile C++ to WebAssembly, to ASM.js. And so this was actual JavaScript. You didn't have a separate runtime. The idea was this was JavaScript that was easy to optimize. And they added these weird annotations like bitwise or 0 to say this is a signed 32-bit integer. And they would use like the unary plus to say this is a 64-bit float. And so that banana bread actually compiled to ASM.js. This is the precursor to WebAssembly. After a while, the browser vendors had implemented ASM.js. I'm like, you know what? This isn't fast enough for numbers. This isn't fast enough for doing like a complicated chess engine in the browser. That was one of the examples back in the day. So they came together and made WebAssembly. And I think it was a lot of design by committee, as in, I think there was a combination of security factors, and also maybe we don't want to be completely tied to the browser. And also maybe we don't want to expose everything. That's a lot of work for us browser vendors who are already doing a lot, and we don't even know if people are going to use this. And so they have that compromise of, we're going to defer a bunch of things to the host, and we'll resolve that later on. There are proposals out there to lessen that gap. So I already talked about the garbage collection proposal, where we say, hey, we know this memory is going to be managed by JavaScript anyway, just give it to the garbage collector there. There's other proposals for passing strings back and forth properly so that we don't have to be copying strings out from one to the other. And there's some other proposals in the works. They don't get as much attention or speed as JavaScript proposals. So JavaScript is moving way faster than WebAssembly. The whole garbage collection proposal was first proposed as they were standardizing it, I believe. And it just got accepted. So it's been around for like 8 years. And they just accepted it recently. I'm not quite sure exactly when. It's really hard to find the dates, but it's not fully merged into the standard. It is scheduled to be merged into the standard. And then you have to have the implementations on both the toolchain side and the browser side and your other runtime side. So there's work in progress to make things better. Yes. WebAssembly is really well supported at this point. So can I use WASM? Some of the old browsers which are discontinued aren't going to have it. So poor Internet Explorer is never going to get it. But it's really well supported. Chrome, Edge, Safari, Firefox, Opera, Chrome for Android. I mean, it's really well supported. And ASM.js is supported by everything because it is actual JavaScript. And so the idea with it was that if you don't have the optimization support, you can still run the code. And for a long time, you actually had a lot of flags in these compilers where they would export both. They would export ASM.js and WebAssembly, and then they would try to use a WebAssembly if you had support, and if the support detections failed, it would fall back. Nowadays, you don't have that. But I remember doing that with JavaScript, and goodness, many years ago.
I'm super curious what you make of the statement from the person at Docker. I think it's like the creator of Docker said something to the effect of, if WASM existed when we already existed when we came up with Docker, we may have just used WASM as the platform.
Yeah.
What do you make of that?
My take on that is, my personal opinion, he's most likely referring to the security aspect, as in it's already locked down. You can't access the file system unless you grant access. What he's probably referring to isn't this idea of, I need to get all these system dependencies built in. So like you make a Docker image, oh, I need the Ruby runtime, and now I need these gem packages, and now I need this command line utility, and I need to install all this. What he's probably referring to is the idea of, well, when we were making Docker, what we were trying to do is make a secure, isolated environment. They wanted that isolation, not necessarily the consistent OS installation. And so that's probably what he's referring to. Would somebody have probably still made Docker? I think so. I think somebody still would have done it for the sheer fact that we don't statically link hardly anything, even though our disks are now large enough we could. And so we're still doing a lot of dynamic linking, and managing all those dynamic shared libraries is a pain. You're still going to have some of that because your WebAssembly runtime probably is relying on some DLL on your system. And at some point, you're going to have multiple WebAssembly runtimes on your servers because you need this one because that's what you targeted, and that's an old piece of code, and you don't know if you're going to break something upgrading it, but you need this other one for this other server because that has this latest proposal. You'll probably run into that at some point. So I imagine that they were thinking of that. But that's speculation on my part. Thank you.